we are lucky that we will listen to his lecture. So thanks a lot, Ignacio.
Thank you.
And please.
Thank you, Fabio. Really, thank you a lot. So, as an introduction, I'd like to say that indeed in the 90s, to be precise, in 92 I was in Aspen. I come from QCD. My PhD was on. I even computed 3 loops in some rules. So I came across a book of neural networks, and I was really impressed by the idea of learning. Now everybody, it's a triviality, but come on, in 92. So the backpropagation algorithm was 86, and I was very, very impressed. So when I came back to Spain, I coded my first neural network. Was very impressed, learning, wow. And then in 94, 95, there was a papers by Shore on factorization, how you can break the RSA codes that we use when we connect with your mail, okay? Elliptic curves, discrete logs, everything. And I learned about teleportation and everything. So by the end of the millennia, and because I also really love philosophy and reading, I came to an individual belief, okay, that there is a transition in how we understand science. And to be very high level, okay, Newton, okay, the first equations, late 17th century, rationalism, beginning of the 17th century, Descartes and all these people. So 18th century is a mechanicist era. 19th century probably is chemistry dominating everything. 20th century we had nuclear physics, okay, the atomic bomb, and we had in our field the appearance of quantum field theory. And then biology, no, the 20th century. But then what is it about 21st century? So in my opinion, okay, it's information. So what is common in neural networks and in quantum information, it's the way that you concentrate on a completely different issue, on information. Okay, unit less. It's not a magnitude like the ones that we are using. There are no units, dimensionful units. So this is why I believe that we are talking about a new paradigm. And today, the first, what I want to say is quantum information as a new paradigm. And just to justify it further, let me try to make 3 lines of how we model nature. Nature it's there, okay? It's sovereign. It doesn't believe in humans, nature. They deliver things. So we come and we want to model what we see. This is what we do, okay? All our models till today have been effective. They have been changed a long time. There is nothing sacred in any piece of the history of humans that has stand the pass of time. Okay, so when we started to think, and I'm coming just from the 60s, there was all the full approach of matrix, S-matrix theory. Okay, and you know the elements that people would be learning at the time was rigid trajectories. Okay, or you were discussing the Veneziano amplitude. But definitely, what we were doing at that time was higher level. Maybe everything is related to fundamental symmetries. And because this is so high level, the fundamental symmetries are only in the observable space. Okay? In the observable space, not gauge symmetries. And then at the time, well, people definitely wanted to have unitarity as a basis. But at that point, there was analyticity and crossing and whatever people would come up with Radiated algebra, supersymmetry would be a piece. Everything that was allowed by the S matrix would be there. So the hope that by a set of these symmetries we would fix the scatterings was a hope. That hope didn't work. As a matter of fact, we know that every field theory fulfills those statements. So it's an underdetermined system. These symmetries are not enough to deliver physics. So you come to a second idea that everything is about a Lagrangian, let me say a Hamiltonian, okay? So rather than just looking at the correlations, why don't you look at the dynamical principle? So that is the idea. You want to recover the equations of motion, okay? After Hamilton, you can elevate that at the Hamiltonian principle. Why don't you tell me the Hamiltonian principle? And therefore, here, we need the symmetries of this guy. Again, so we have symmetries, okay? And in particular, gauge symmetry. But when we constructed this series, it was a big mess. There were infinities, and we have to learn things like the renormalization group. Or we had to rephrase some of the observations in terms of non-trivial symmetries, like conformal theory, okay? And then a new era came that, can you classify those things? Can you completely determine all the properties of conformal symmetry? Can you have at least one subset of the Lagrangians in the world that are fully characterized by a symmetry? Conformal field theory. Was very, very, it's very, very nice, no? And we come from here, no? All the discussion today, how you compute T bar. You use a field theory, quantum field theory. But suddenly, there was a new player, the wave function. So why do you care about the symmetry? Why do you care about a dynamical principle? Why don't you go back to the essentials and discuss what is the wave function and what can you do with it? So actually, I don't care whether there was a Hamiltonian or a different Hamiltonian that delivered a state, but here is my state. What can I do with it? Suddenly I can do things with the state, which are completely unrelated to any Hamiltonian. So I can do teleportation. I can take a quantum state, all the information in the psi, and send it to another place by a very clever algorithm. I can do quantum communication, quantum key distribution. I can do quantum computation. So what I'm doing is that I'm simply seeing the system. I go down to the system and see the wave function, and I manipulate the wave function, and I extract some useful stuff. Much closer to engineering. It's like accepting that you went through all that, and finally, okay, we understand, let's exploit it. Okay? So this is what many people did. But there were many surprises there, many. So we understood much better non-locality. Non-locality was a big thing. So all the Bell tests, be clear, okay? Entanglement is not a Bell test, okay? Bell test requires many extra assumptions. We will talk about them later. Or people got crazy and said, are the rules of quantum mechanics final? Is the final theory? Is Einstein right? And we have an incomplete theory. So what are the limits? And people started to discuss other ways, so generalized probability theories. I will only say one thing about that. There have been, in the last 10 years, really spectacular things. Well, spectacular, let me say, very, very deep thinking about that. I was thinking of an analogy, okay, yesterday. I thought, look, we are in Firenze, so we have information, observables of all the time that people take to come from different cities. I collect these things. Can I understand better what is Italy with that? Okay, well, I may learn something, no, that it takes more time from Sicily than from Bologna. No, I start to gather information. May I see some symmetries north, south? I don't know. Another idea is, no, I take the equations of motion of an engine, I produce what is the speed, and I know that there are constraints. Okay, there are constraints on whether I took this road, and I can predict the time. So these observables, now I can compute them. Okay? And here, the idea is, come on, I don't care about this thing. Give me the trajectory, all the trajectory. So think of it step by step. Then when you understand the trajectory, say, hey, you see, you lost a lot of time here. Why don't you do the other path? And in a way, you are defining a quantum computer. I'm changing the unitary locally to get what I want. Okay? So I'm utilitarian. I'm looking at the actual position as a function of time. This is what I'm doing, okay, in classical physics. Okay, but here there were a number of surprises. Let me mention two of them. One is, what about, comment, what about the postulates? Can we remember what are the postulates? We never do that, no? We always publish only. That's the only thing we want to do. We never go back to the postulates. Let me go back. Remember, in the 1930s, Johnny von Neumann wrote a book with the postulates as we teach them today. Postulate 1 says that all the information in the system is in a ket. Okay, let me forget about the rays and things like that. It's a Hilbert thing. So I define the language. Postulate 1 defines the language. This postulate does not exist in classical physics because we give it for granted. The position of a particle is R of t, and it belongs to R3. But in quantum mechanics, because it's not an obvious theory, we write it down. Second, what is unobservable? Unobservable is an operator that is self-adjoint. Let me again try to write it like that. So I define what is observable. Postulate 3, if I measure, the result of a measurement is probabilistic. So no determinism according to quantum mechanics, and given psi I'm measuring A, simply A psi square. Of course, here the norm of psi must be 1, so that I guarantee that the probabilities add up to 1. And also, after measurement, psi collapses into A. Okay? It's an update of information. There is no physical transmission of energy. Okay? I collapse in all the universe because it's information. Okay? There is no transmission of energy. And the P4, which is often written as the Schrödinger equation, no. Psi of t is obtained as an operator from psi of t0, and this operator is unitary. I postulate that time evolution is a unitary thing. And now I'm asking you, where is h bar? Postulate 1? No. Postulate 2? No. Postulate 3? No. Postulate 4? No. No h bar. So if you think carefully about quantum mechanics, it is telling you what is the theory you have to use to do computations. It's only when you go down to a particular system that suddenly you say, oh, my system is x and p. Okay, and the operator is x, and p is minus I, derivative of x. And now I need dimensions, h bar. Okay? Or when I say my unitary is driven by a principle, suddenly here I need Hamiltonian because it's self-adjoint, okay, h bar. So h bar enters when you specify the model. But if I go back to the 4 principles, they all talk about information. All the information of the system is in a ket. It's a postulate. I cannot prove it. I'm postulating. If wrong, nature will tell me it's wrong. Second, how I make contact with observable. Not everything is observable. Again, what information I can retrieve is limited. Third, I update information after measurement. And fourth, probabilities are maintained. If the first ket was with norm 1, after that it will be norm 1. So the probabilistic interpretation of quantum mechanics is maintained. Okay, so the postulates, look at them again, are postulates about how to handle information. Okay, this is what they are. It's a high-level way of defining what are the limitations that you have to obey. Now, all this discussion may be, I don't know how to say, it's less trivial than you think. And I will give you only one example, which is that the state depends on the observable, because it's the information handled by the observable. So I propose you an experiment. The experiment is the following. Alice and Bob, two people, start with a cat. They agree they have generated parametric down-conversion, so they know what they have. And this state is 1 of the square root of 2. Spin up, Alice, spin Bob. Bob minus down, Alice, up, Bob. Both, they agree. This is what they share. Alice and Bob are space-like, so they are really far apart. And they agree on the following experiment. At time t, Alice measures in the base of sigma z. She may find a spin up or a spin down. And the proposed experiment is the following. Right after that, so time plus epsilon as small as you wish, both Alice and Bob, write on a piece of paper, write the state for Bob. This is very clear, huh? I am here, there is somebody in Singapore. We share with satellite. By the way, we're building a satellite in Singapore to deliver entangled pairs in the planet, okay? With tracking stations in different countries. So we have taken to height that we never thought quantumness, okay, to the satellite. So we do that. We receive the entangled pair, and we follow that. And now, let me be Alice and let me be Bob. Okay? So Alice measures. She measures down. And now she writes the state for B. Okay? So what is it? So she says the state for B, according to me, to Alice, it is up, a pure state. Okay, she knows. She has an update of the information in the universe. So she knows that state is up. Whereas Bob, he doesn't know about the measurement. So the only thing he can do, Bob, is to say, look, I don't know. So it can be anything. So it's 1/2 of up, plus 1/2 down. So you see that at the very same time, two different observers have two different density matrices that describe the system. So I don't know why this is never taught, but this is a way to understand that the description of nature depends on the observer. It's the observer that's saying. We are so used to working a given basis that there is no discussion. But sensu stricto, things depend on the observer. Okay, there is another. This was towards the fundamental aspects of quantum information. We are rethinking carefully these things. But there is another thing I would like to tell you. Anything I do here, any experiment, requires precision. So it requires to preserve the quantum properties. So requires to preserve coherence. Because otherwise, we lose all the things. And this is not easy. If you think carefully why the experiments we have now happen, is because there was an enormous progress in the technology of lasers and of cold temperatures and of all these things. We have parametric down conversion. Somebody mentioned that you have 200 standard deviation. There are many more. You take a femto laser, you do parametric down conversion for a few minutes, and you go very far away. So you verify Bell inequalities far beyond the 200 standard deviations. This is because of the improvement of the instruments. Now, if it is so difficult, there are a number of things I can extract. Well, first, if I do it, quantum computation will be difficult. So the manipulation at will of anything will be very difficult, will not be easy, because decoherence is killing your state. This is superconducting currents. There is a problem of decoherence. Ions have longer decoherence time, but the operations are on the microseconds, so you don't gain a lot. So systematically, the decoherence is the problem for quantum computation. But photons are okay. Photons, free photons are okay. So why don't you use quantum communication? So quantum communication is a macroscopic experiment, I mean, with distances which are amazing, that we can do because photons do not interact with each other up to the box. And so they preserve well their properties, and you can now, if somebody interferes, I can check. So the idea of detecting if in quantum communication is that the wave function is collapsed. And therefore I can check that somebody interfered. Okay, so I can do that. But please be also clear that when something is very difficult to preserve, it's because it detects everything. So by definition, a qubit not only can be used for computation, can be used for quantum communication, but it can be used for quantum sensing. Okay? Because it's so fragile. Okay? That's why we are having now the best sensors. And sensors is an extended idea. So for instance, clocks are within the category of metrology and sensing. And we are now building clocks of 1 part in 10 to the 20, okay, with ions and with different techniques. Or we have now gravimeters of a microgal precision, so 10 to the minus 11 times 9.8 meters square second, 10 to the minus 11. So actually you can map gravity. Now many countries are doing, we are doing that in Singapore. We are mapping gravity with a precision that detects any back of gas, any tunnel, anything, okay? Or we can, or the first flight, GPS deprive was done this summer with NV centers. Okay? First time that you fly without GPS, because you are reading the magnetic field of the Earth. You decouple the inner core from the crust, from the equipment in the plane. So you use machine learning to decouple these things, and now you can fly. Okay? Very impressive. Because the ultimate control of individual qubits, okay, individual elements in quantum mechanics, is that amount of fragility and therefore to sensing. In this sense, this is a community I've been preaching for years without any success. I think we are still in a level that we are using classical physics to measure our quantum systems. It is time that we move and we make detectors which are quantum themselves. Okay? Think of using Bose-Einstein condensates to detect particles that arrive. I've always wondered whether you can do that with neutrinos, okay? Because you have phonons that may have the wavelength, and you have a prefactor that is n atoms, that when you square is n squared, and if you have 10 to the 15 atoms, the response is multiplied by 10 to the 30. So why don't we go to refining our measurement apparatus and make them quantum, not classical? Okay. We still see drift chambers, we still measure electric fields. Why don't we go to the quantum level? And this is done, by the way, in quantum computation. When you read out a qubit, you are doing it by the laws of quantum mechanics. So the resonators that read are quantum. Okay. Okay. So this was a very long introduction, but I think there were a number of things which are not completely obvious. Let me now start to build towards, the purpose is to have observables in high energy physics. So let me start to build up the figures of merit. You have seen the talks, how people use that. Let me repeat some of the things. Let me also introduce new figures of merit that have not been used. Okay? So we need to make an effort in this direction. And that is tantamount to quantify entanglement. So let's just try to quantify entanglement. So the very first thing is that entanglement is associated to the superposition principle, just when you have more than one particle, okay? And you cannot write that superposition as a product of the superpositions. But this is a little bit naive. So if you have pure states, it is very easy that, well, you will see that we can do that, but in general, we don't have access to pure states. So give you the example. In the experiments in quantum optics and in other fields, the big thing is to measure entanglement, just like in particle physics, we are analyzing the scattering, okay, cross sections. Well, it's a privilege of those experiments that they can do tomography. So what they can do is to measure all the operators in each element, okay? So sigma x, sigma y, sigma z, and the identity. So when you have n qubits, you have a total of 4 options for each qubit. So tomography is tantamount to 4 to the n experiment. So it's an exponentially hard task to get the quantum state. This is done, okay? This is done. There are techniques now of how to simplify, how to use ideas of very efficient sampling, okay? Actually, many of them come from image treatment, and people are improving on that, but still we need that. The big thing that is that entanglement is always described as the impossibility of writing something in this way. So if I can write a bipartite state as a state for Alice and a state for Bob, but those can be I, different states, and I do that with a classical probability PI, this is how I generate the state. So what I do is I throw a dice, I check, oh, the 2 is 1 time, so I prepare that state. If I throw the dice another time, I get another, I prepare the other. So the probability distribution of the dice is a classical distribution, and I build that. How can you do an impossibility proof? How do you prove that? Just to give you an example, this is not trivial. This is not trivial. This problem has only been solved, okay, for the Hilbert space of C2 cross C2 and C2 cross C3. No other Hilbert space, okay? We have a solution that is simple. Actually, we can prove now that we have an infinite number of constraints to detect whether the state was entangled or not. And just to show you the complexity of this thing, the basic idea was introduced by Perez many years ago. And what you do is the following. You take the density matrix, so I'm giving you a system 2 by 2. I have 16 numbers. I give you the 16, they obey that, they are self-adjoint and the trace is 1. And given those numbers, tell me, is it entangled or not? Well, what you have to do is the following. You have to build from rho, which is given by, and now I'm very explicit with the 2 states in Alice and the states in Bob. So this is the states, the density matrix in Alice and Bob. Sorry, here I should have written rho B. Sorry for that. So this is rho A, this is rho B. This is the probability. I invent a thing which is called the partial transpose, and this is written like that. So what I do is a partial transpose on Bob, okay? When you do that, if the state that emerges is positive, if rho trace of B is positive, the state is separable. If not, it is entangled. And this is the only simple way that we have nowadays from the density matrix you reconstruct by tomography from all the sets of experiments to decide whether the guy was entangled or not. Of course, if you assume it is a cat, then it's simpler. But if you want to make contact with experiment, you have to go through tomography. Okay? And this is not simple at all. People have tried to find something similar. It's completely impossible as of today. Okay? There are another property that is related to quantifying entanglement, but now for the pure states, which is that you may be given a state like that. It is given by alpha 0, 0 plus beta 0, 1 plus gamma 1, 0 plus delta 1, 1. And I ask you whether this can be written, question mark, plus A 0 plus B 1 for Alice, okay, times C 0 plus D 1 for Bob. So is it possible? And you can check that this is only possible if alpha delta minus beta gamma is 0. Okay? So for a pure state, it's much simpler. Either those four numbers obey this, and if they obey that, it's a separable state, or else it is entangled. And so that brings the first figure of merit. And this is called concurrence. So the idea is that if I take C equal to 2 times alpha delta minus beta gamma, this is either 0, and it is bounded by 1, and by 0. 0 is a product state. Anything beyond that is not a product state. And you have this idea that maybe if I grow the concurrence, I'm getting more and more entangled. Okay? Now, I'm unsatisfied with that. So can I elaborate a little bit more? Are there other ways of doing that? Yes, and people have done a lot of efforts. So let me mention two in particular. And I would like to mention that one of them was the preferred figure of merit by Parisi. I don't know if you know, but Parisi has written many papers on entanglement. So the idea is there are other figures of merit, and besides concurrence. So one of them is the following. Simply take the reduced density matrix for Alice. So I trace Bob. I do the reduced density matrix. And this reduced density matrix, I take the square and the trace. So it turns out that you can check that if the state is pure, then you would have, if it is a product state, the reduced density matrix is pure, the square of it is itself. So if you have a pure state, and I take the square, so this goes away, is a 1, so rho square is rho. So if you are pure, if you are a product state, rho square is rho, and therefore trace of rho is 1. So if I go to 1, it turns out that I have a separable state. Then if I'm less than 1, I have entanglement. So for instance, Parisi wrote a paper analyzing states which are multi-qubit and checking random states, how much entanglement there was in average. Okay? And he used the purity as a figure of merit. And you can show that in average, when you throw a stone into the Hilbert space, the average state you hit is maximally entangled, almost maximally entangled. So entanglement in the Hilbert space is the most frequent thing, not the exception, okay? And there is another figure of merit, and I wanted to mention it here. And this figure of merit is a von Neumann entropy. Another figure of merit is the von Neumann. This is purity, okay? This is the purity. And finally, the von Neumann entropy. Well, this is a little bit more crazy. What you do there is that you take rho, you go to rho sub A, so you take the reduced density matrix, and now you do the following operation. You take the trace of rho A, log of rho A. So it's a nonlinear function of the density matrix, okay? Why this is so? Well, you can check that the von Neumann entropy is it's a minimization of the all possible classical. So it's a minimization of the classical entropy, the Shannon entropy of the PIs that construct the state. So I don't want to do it now. But there is a relation with information theory from 1950s. Okay, that's the very first thing. Remember Claude Shannon, 1950, he establishes the theorem 1, 2, all the theorems of information theory, and only the complexity comes in the 70s. Okay, it's the story of information theory is 30s, computing is physics. Okay, the fathers, Post, George, all these people. Then you have Gödel, then 50s, Claude Shannon, the operational theorems, then 70s, complexity of computations, okay? So how you compute that is not trivial. So what you have to do is to diagonalize these in terms of some eigenvalues. And when you have these guys, you simply compute sum of lambda I log of lambda I, okay? Because you can check that any expansion of the log, you can now take U dagger, and they cancel all of them, and because of the trace, they cancel cyclically. So the eigenvalues are tantamount to that. So that means that this figure of merit is extendable to every number of qubits, okay? You can take the reduced density matrix. It is not a 2 by 2. It's not a case of Alice and Bob. It's more generic. You can even think of a system with very many and start to see the density matrix for 1, for 2, for 3, for 4, and see if there is a scaling of entropies or things like that. Okay, that you can start to do. Not only that, but it contains information of all the eigenvalues. People have realized that the phases in condensed matter are related to this distribution of eigenvalues, and in general, people call all these lambda i's, you take minus log of lambda I, you call that EI. This is called the entanglement spectrum of a theory. So you give me a theory. I want to understand it in detail. I do that. I take the reduced density matrix, I take the eigenvalues, I take the logs, and that is the entanglement spectrum. You can prove, for instance, that if there is a topological phase, there is a gap in the spectrum. So suddenly you start to see properties that are very, very powerful related to the distribution of eigenvalues of the entropy. Highly, highly non-trivial, all these things. Okay, since I know I'm okay. Yeah, I'm okay? No, I'm late. Okay, so let me then concentrate. I wanted to say something about T plus, T minus, but I will say on the third lecture. Okay, I will. I have postponed that thing over there. And I wanted to say just one thing that I hope you would like. I want to make a final set of comments on non-locality, okay? So let me do it. So when you check nature, and you check correlations, and you check entanglement, can you do better? Can you check more things? So I want to understand what really is quantum, okay? So I want to understand non-locality. now we go into the heart of Einstein criticism to quantum mechanics. So let me remind you of the Bell inequality very briefly. So the setup is, again, somebody prepares a state made of two particles. You have Alice, you have Bob. So Alice and Bob decide to measure, and they choose in the spot what they want to measure. So when you deal with non-locality, to avoid hidden variables, you have to give the freedom that non-local, space-like events happen. So the guy decides, the other guy decides with no correlation, okay? So they decide to measure. So Alice decides to measure in the direction n, and Bob decides to measure in the direction n prime. So there is Stern-Gerlach experiment and a Stern-Gerlach experiment. And they agree on a number of things. If they both measure in the same direction, they keep observing that they have the opposite result, this result being, in general, only plus and minus 1. So whenever Alice measures 1, Bob is minus. So with hindsight, we are preparing a singlet that we usually write like that. So they observe that. So they accept that that correlation exists. Okay? And now it turns out that if you don't believe in quantum mechanics, but if you believe in local realism, whenever I compute anything, so this is local realism, I believe that whatever I measure, it was predetermined. It's not a random. There is no randomness. It's deterministic. So the way to do that is that the system may have a series of hidden variables that are distributed in whatever way. I have a probability distribution for the hidden variable. But now Alice will have this hidden variable, and then n. And Bob will have this hidden variable and n prime. So local realism says there is no determinism. There is a clock telling me if this is the time, you should be plus 1. Okay? And this hidden variable, okay, dictates what it is. But how do you do it? What is the hidden variable in an experiment of spins? So do you know? You don't know, no? So the difficulty is, okay, this is a fantastic formulation of what is local realism. This is not the way we compute in quantum mechanics. We compute with a ket and with sigmas, and we do another thing. But what would happen if I accept that? And here's the famous combination of experiments that was suggested by the CHCH, okay, Clauser, Holdwell, the people that now, the Nobel Prize of 22 was given to all these efforts, okay, Aspect, Zeilinger, all these people. Well, they made the observation that if you end up measuring 1 or minus 1, if this is predetermined, well, then necessarily this guy can only take the values minus 2, 0, and 2, if there are nothing more. But in the case that this is 2, that means that this is 1 and 1, but then this is 0. So in any combination you do, the absolute value is less than 2. Okay? And now, here, quantum mechanics has a completely different recipe. It's a different model of nature. It's humans writing how to compute observables in a different way, don't care about all this construction, and simply says, man, if you want to compute that correlator, A and B and prime, and you are quantum mechanical, man, you take the singlet, you take now the operator sigma times n, operator sigma times n prime, and psi minus. And you compute that, and you get minus n dot n prime. That's quantum mechanics. So, you know, the local realism says that, I say that. Okay, now comes the choice. Alice and Bob decide all this. directions. So the quantum mechanical guy says, if Alex chooses the two axes like that, and Bob decides 45 degrees tilted, all these angles, well, this with this is 45 degrees, this with this is 45, this with this is 45, and one of them, it's minus 45. So you end up, for the CHS H, I end up having 1 square root plus 1 over square root plus 1 over square root. And now the critical minus sign for this becomes minus 1 over square root, because I chose very cleverly these things. And I have 2 square root of 2. And this is a violation of 2. So that proves that our theories cannot be expressed in terms of the hidden variables. And to prove that, we need non-locality. It's not enough entanglement. So if you look in detail, what are the key elements for the Bell test? One element is entanglement. Without entanglement, no violations. But the second element is that the set of operators in Alice and Bob's, so that the operators that you have there, and the ones at Bob, they do not commute. So what you need is to push classical physics. So I take observations that do not commute if they were in the same place. And by pushing quantum mechanics in these two directions, on entanglement, maximal entanglement, and that the observables I measure are not compatible, then I push quantum classical physics to the point they cannot respond to these correlations. That is the source of the Nobel Prize of 22, and it was a number of people that work in this thing. You may know that the first experiment is by Wu, by the particle physicist in a separate entertaining job. She checked the very first thing without adding the possibility of switching things. So she never got to the Bell inequality because she was fixing the outcomes, okay? And this was by that fantastic woman. So here comes what I want to shake now you. See if I can. So it's fantastic. Now we are understanding that the world is quantum. It is not classical. It is not deterministic. It is not like Einstein liked it. So let me make it like that. Imagine a space where I have correlations. So the Bell inequalities, I may think as a polytope that has faces. So the Bell inequalities tell me if the correlations are inside, I'm in the classical world. If I'm outside, I'm in the quantum world. So the Bell inequalities separate me from what is genuinely quantum, from what is classical. So I ask you, is this the final thing? Can we push? Can we think of the following? Is there any way we can build an experiment that pushes not the classical frontier, but the quantum frontier? Can we say that the world is quantum and not beyond quantum? And as you see, everything is related to correlations and how non-local these correlations are. Classical physics cannot have that much non-locality. Quantum mechanics have more non-locality. What about nature? Can we do an experiment which is completely blind and checks whether quantum mechanics is correct or not? And I give you a possible theory of the universe which is not quantum mechanics. It's a very abstract thing. I will not present it. It's the following. It's an idea of non-local machines, but the idea is that Alice and Bob, again, have something that they push, and X and Y will decide which experiment is performed, and they read A and B. So the only thing I have to discuss is the set of probabilities of AB conditioned by the preparation XY. So now I'm hitting the real thing. What is the description of nature is how general these probability distributions are. The more general, Let's exploit that. Quantum mechanics is definitely a subset of that. So it turns out that if you give as a rule that the machine, which is highly non-local, delivers the following output, A plus B is equal to xy. It's a very silly thing. It's called a non-local machine. So there is no other thing. I have a rule when these probabilities are 0 and 1. You can check that you put this machine, and now you translate into probabilities, and you go to the Bell inequality. You get not 2 square root of 2. You get 4. So you have an embedding, which is 4. This is 2 square root of 2, and this is 2. But you prove something else, that never signaling is violated. So all these theories do not violate causality. So you could have thought, oh, quantum mechanics is non-local, but it never violates causality. Maybe this is a key to quantum mechanics. It simply is the ultimate theory of non-locality without violating causality. Well, this is not true. So these non-local machines do not violate non-signaling causality, but they give the CH operator a value of 4. So it is now possible to go to experiments and do this experiment. So the best experiment I know myself, okay, was on Singapore, by the way, many years ago. And what they did is that setup. But now you push to the limit. So you do a random search in all possible states, in all possible observables, and the result is the following. So according to the experiment, the maximum violation they observed for the CHS experimental was, let me give you the number, 2.82759. It's an amazing precision. The reason is this is done with parametric down conversion. Okay, as I said, with BBO crystals. So it's extremely efficient way of generating entanglement. And this was the experiment, and the quantum mechanics maximum is 2 square root of 2, which is when you subtract, so 2 square root of 2 minus this thing, okay, it is 0.00008451 within quantum mechanics. So we now have certain evidence that nature has not more non-locality than the ones that quantum mechanics allow and describes. So according to the latest, okay, quantum mechanics is sufficient. It's sufficient. We don't need another theory beyond that. Every non-locality that is inherent to quantum mechanics is describable by the postulates of quantum mechanics. We have this observation of the limit, okay, of that. Let me add that the recent efforts in the last years was, okay, so classical is determinism, hidden variables, so everything is prescribed. 4 is causality. So what is 2 square root of 2? What property of nature dictates 2 square root of 2? So I have many papers of people looking for something, a physical property that tells me why nature is 2 square root of 2. And all of them have to do with protocols of doing things. So it is as dictated. The laws of nature are such that it is allowed to do this thing. But there is no clear cut. There is not single principle. Nobody has gotten to the 2 square root of 2 from a higher principle. Okay, nobody has been able to characterize that. So we have locality, we have causality, and we don't know what is in the middle. Okay. I finish here, and what I wanted to do very humbly then is an analysis of 3-body scattering, so to see beyond 2 particles, how 3 particles get entangled, and why these scales and condensed matter physicists have worked a lot with this. And then in the last, I would try to show you computations in QED, the profound relation between the Lagrangian of QED with maximal entanglement. I will try to show you that analytically. Okay. So if there are questions, there were no questions. I'm sorry. It was intended to be very dynamical, but sorry. Sorry. Yeah. Tell me.
Thanks. This was very, very interesting. I just have a question about this experiment. So
I think it doesn't work. Huh? Yeah.
it is on. No, I think it works.
Oh, yeah.
Yeah, it does. So about this experiment, I mean, clearly, okay, the result is very close to 2 square root of 2, but could it be that there are some limitations of the experiment itself that prevent us from measuring a higher value? And if we think of, I don't know, maybe a better experiment, we can actually measure higher value?
This experiment was never intended to be a loophole-free experiment, okay? So there was no intention of guaranteeing that they are space-like, or, you know, people have done anything with this inequality. You have relativistic violations. Gizen made particles to go closer to the speed of light and check. People have tried zillions of things. The fundamental loophole is definitely the non-signaling between the parties, okay? One of the experiments was done with envy centers created in Delft, and they created the pair, and they carry the pair to some other place, and then they measure very spectacular things. This experiment was done to improve to randomly explore the possibilities of the experiment, so the directions and the states, with an extremely high luminosity, you would call, to get a lot of decimal places. That was the spirit of the experiment. And you have to take it as such, okay? It's not the best experiment for proving the non-locality. It is the most accurate experiment for checking the boundary.
Mm-hmm. Okay.
Now, you're right. Anything can happen.
Yeah, I was just trying to think if we can...
Yeah.
I just don't know this experiment. Perhaps we can think of another one that might, you know, in some sense.
Look, as I said, every time people are checking one loophole, there is an experiment by Zeilinger, which is, I find it very funny, which is Alice and Bob have to choose between NA prime, and NB, and NB prime. How do they do in experiments? They do a random generator. But come on, this is not a random generator. So some people started to use a quantum experiment to measure and decide the direction of the next experiment. But Zeilinger did something different. He took light from the cosmos in opposite directions. So in order for somebody to have thought that the two photons that arrived there and they decided the directions, they should have been prepared 700 million years ago. Okay? So this is to rule out the superdeterminism, but you will never be able to rule it out, never. Okay? So every experiment is trying to push the boundary in one direction. And this was the precision of the Tyrrell-Solon bound, which is the name of this thing. Okay?
Okay, thanks.
Mm-hmm.
Hi.
Alberto, hola.
Hello, Ignacio, thank you very much for this very nice lecture. Just a comment, you mentioned that you can use von Neumann entropy to explore entanglement of multipartite systems, okay? But still you have to compute the von Neumann entropy for each bipartition, is that right? Yeah, this is related to the ideas of renormalization group. So if you have a phase transition related to conformal symmetry, you do expect that the system will develop scaling laws. So this idea of checking the reduced density matrix for increasing size is really aligned with the phase transitions, okay? Now, if you are Puritan and you really want to understand entanglement, I will show you that already for 3 qubits, there are 5 invariants. Not only the reduced density matrix of the 3 guys, but 5. But actually, the number of invariants grows exponentially as you have n.
particles. So quantifying entanglement is an impossible task. There are exponentially many figures of merit that tell you something about entanglement. And typically, what are the tasks you can do? So can Alice and Bob do something to send information to Charlie? Well, this is measured by some figure of entanglement. But as you increase, there is a combinatorial explosion. And on top,
even for a pure state.
and then even for a pure state. And even, I will show you, that even there is a mathematical piece that goes transformation. And there are the books of literally 1890. And it turns out that there is a surprise for you. There are invariants that cannot be formulated from the reduced density matrix, that they really take the state as a whole. And those are very complicated. The tangle is an example. The hyperdeterminant is an example. So quantifying entanglement beyond two parties is exponentially harder. Okay? And it has a meaning. The tasks you can do depending on that entanglement are different. So it has an operational meaning. Okay? It's very, very subtle. Some mathematicians have gone there crazy. Yeah?
Thank you.
I mean, this Bell test with photons was somehow, we repeated that with mesons in an E plus E minus experiment. And there you have a problem. These mesons are not no stable particles, so they decay exponentially.
Yeah.
And then if in order to make this Bell test, you have, of course, to renormalize the coincidence, I mean, by the exponential decay. And this was somehow heavily criticized that you are not able to do that.
I myself, I think, criticizing privately these things. You see, the Bell test needs that Alice and Bob can choose two bases.
That's okay,
So what do you do there? Because in one base is natural, in the other, what you do reconstruction, you put matter and you rebuild the bases depending on you want CP or you want the other, okay? And second, the second base in Bob should be like that, should not be the same basis. Then there is no violation. You have to twist it. They have to be incompatible. I don't know how to do that with Bell, with B particles. I don't know. I mean, you may argue there is entanglement, but the violation of Bell inequalities is a tall call, and I don't think you can do it, I think, okay? I may be wrong, maybe people disagree. But I repeat, the two elements is entanglement. Okay, given, B bar has. Second element, Alice measured in two bases, and what are the two bases for you? And second, Bob, in 45 degrees. How do you do that? How do you do that? So it's not at all trivial.
Well, I mean, I certainly agree that you cannot predetermine the measurement because
You should.
This is
Bell,
not possible.
but
Bell,
that's,
I
this
mean,
is not the right system to
but
check Bell.
I mean, there is a possibility, but this is experimentally.
The point is that
so
Bell,
difficult that you
Bell
never
is a monument of science. It distinguishes between classical and quantum. The fact that this is done easily in some systems and very difficult in other systems is a separate issue. So BB bar is not the system to check these things. Okay, that's my opinion. Because you don't have the freedom of the experimenter. It's a place to check entanglement. Entanglement is fine, but not Bell.
No, there I agree. I mean, freedom of choice.
You should
is
be
not given.
clear that you can describe entanglement in classical terms in many situations. You don't need quantum mechanics. There are many examples. Okay, you can represent that. The very fact that quantum is not classical requires the non-locality. And this requires the test. And this is the genius of John Bell, by the way, at CERN. I mean, it's always very shocking that he was there. And this is the key. As I said, Wu, the one of CP, she did the experiment without this thing. So she could never claim anything like Bell inequalities. Okay? So you have to be very clear about that. So the claims that in particle physics can be done, in my opinion, are related at the moment about entanglement, not about Bell. Okay, you agree?
I agree.
Yeah. Good. Yeah.
Hi. I have one small question about the postulates because I don't know I want to know what you think. Because in the postulate 3, you postulated that the wave function collapses, right, to the state.
It's the information collapses.
Yes. And then in the next postulate, you say that information is conserved by unitarity. So how can you reconcile the collapse with unitarity?
Absolutely. It's from the point of view, well, let me use the Bell. You know, Bell used at CERN used to explain these things with the shoes, you know, with the sockets of Bertelsmann. I don't know, you guys, all guys, you know the story, no? I'm not kidding. So Bell used to explain it like that. Bertelsmann used to be a special character that every day he chose randomly the sockets. And if one was blue, the other was red. Okay? Next day, it was a round, or there were the two blues or whatever. But he was always different, so always blue and red. Then he said, the moment I see one of his legs and I see red without looking at anyway, my universe has collapsed. I know the other is blue. Okay, so this is the hardcore thing. This collapse is produced in the information of the observer. Remember that every observer has a different formulation. So that observer that made that measurement, he knows that thing. This collapse involves no energy. It's information collapse. Okay? Is it clear? I mean, so the fourth postulate is the dynamical principle. It's how time evolves between measurements. And the only thing it says is that you will not lose probability. And therefore, unitary evolution is necessary. Okay? If you write it as, by the way, if you know very well, if you write it as I did with a unitary and then you put exponential, then you take the differential thing and you get the Schrodinger equation. But this is a particular case. Any unitary evolution is valid in quantum mechanics. You don't need the equation, the Schrodinger equation. This is assuming a Hamiltonian and no need for that.
But there is something there which is strange, right? Because you are, the measurement plays a central role.
Okay, now we go deep here, okay? The measurement. So what is the new ideas? Well, many people think, I do think, that there is nothing special in measurement. So what we have lived is 100 years, where we couldn't do anything. The measurement was instantaneous, because when a photon enters in a crystal in 10 to the minus 18 seconds, paf! And we didn't have any machine to check what the measurement is. So there are now experiments at Yale where they are opening the box of the measurement. And guess what? Everything looks unitary. So this collapse of the wave function, it's probably a magnification of a small thing that goes towards, people call it a pointer state, is the name they call. So this idea that measurement is a complicated thing, no. It's simply a system where a small particle interacts with a large amount of particles. And the typical behavior is that there is a very rapid transition to another state. So think of a photon multiplier. You enter with a single photon, poof, you end up with, you magnify the signal. Think that the apparatus of measurement as a magnifier of whatever little thing is there. If that happens, philosophically, we are back to determinism. Okay? So Einstein would be happy. Well, if you like it, but I don't like why do you need many-world theory? I don't understand. Man, everybody says, but why? Yeah, that's it. Yeah. But I don't need the interpretation, okay? I follow my universe, that's it. There is only my universe, it's unitary. There is never probabilities there. So, just to complete it, there is a really spectacular line of research on opening the box of the measurement apparatus. Beautiful thing, okay? Yeah. Marco, come stai?
Bene. It's a vague is it correct to think that you need a probabilistic theory in order to reconcile non-locality?
Relativity.
Yeah, I mean, the fact that you, even if the interaction is not local, you are not sending any information. Is this thing essential?
No. As I said, this machine, which is a probabilistic theory, it's a generalized probability theory, obeys non-signaling, therefore consistent with relativity, okay? And that it's beyond quantum mechanics.
Right, but it's a probabilistic theory. My
it's
question
a probabilistic theory, yes.
Theory. You see my question?
No, but this is all the correlators here are +1 or -1, so it's deterministic. It's such a simplified version that this law, when written, can only take values +1 or 0 for the probabilities of plus, minus, plus, get +1, and the other minus. So it's deterministic. Okay? So it's a beast, this guy. That was invented by a guy, and it has been used to show this polytop structure and this space for all the generalized theories that you have there. Okay. Mm-hmm.
Sorry, maybe I'm wrong. You said that you do not care about interpretation, but to me it seems that you are embracing the quantum Bayesianism interpretation of quantum mechanics, because at the end what you are saying is that the wave function collapses is just the information collapse, and which is relative to the observer, which is nothing else than quantum Bayesianism.
Well, in my presentation, indeed, I'm the official Bayesian interpretation of quantum mechanics, although I hate the word interpretation because no equations change. Okay, this is my problem with the word interpretation. There is no observable that can distinguish between one. No experiment can distinguish between two interpretations. Okay, that's the first thing. And I agree with you that my presentation was a Bayesian thing. It's an update of information, and therefore it's Bayes' theorem. Now, to be honest, I believe internally that we are in this stage of quantum mechanics that everything was effective, and the measurement is an effective description. So I believe that there is an inner description of that then would eliminate this update, Bayesian update. Will simply be deterministic, so evolution in time, unitary evolution, and therefore there is no Bayesian thing. Okay, which I do believe that. Let me say, this is less and less ridiculous because the Nobel Prize of 23 the 22 was for Bell. Bell should have gotten it, okay? He was shortlisted the year he died. So the 23 Nobel Prize is for the control of attosecond experiments. So we are getting into a realm where you may know that now there are experiments where you see ionization of an atom as a dynamical process, because the time scale of 10 to the minus 18 seconds is the natural scale. So this idea that we take the Schrödinger equation and we solve the stationary states and we do everything with the stationary state is becoming obsolete. So now people have even observed double ionization in an experiment, step by step. By the way, I don't know if you know that they are reproducing the step of particle physics. How do you see these things? They have to put a field, they have to curve, they have to... They're reproducing an accelerator for these things. So the 10 minus 18 second, that's the new limit. So all the new physics that is awaiting for us, 3 orders of magnitude better than a few years ago. And that's great, I would say. Let me say another place where quantum mechanics finally was much simpler than expected is all the paradox of information in black holes. You know, the discussion, you fall, the information, you evaporate as a white noise. Where is the information? So the accepted solution, okay, was, okay, that there is no loss of information. You simply have a unitary evolution of the full system that we don't know how to compute nowadays, but it's unitary. And it has been argued that the holographic principle is the proof. If everything which is done with gravity can be mapped to theory without gravity, come on, the theories without gravity are unitary. They don't lose anything. So if there is no loss in the boundary, there is no loss in the bulk. So again, this is a place where people have reasoned that the traditional quantum mechanics was good enough, okay? No need for crazy ideas. Mm-hmm.
Hi, I would like to come back to this particular example, this 2 square root 2 as a prediction of quantum mechanics, because you gave this other example where you can go outside of 2 square root,
yeah.
right, 4. I mean, would you be able to pinpoint what is different in this theory from quantum mechanics when you get 4?
Yeah. This theory is just an absolute non-local machine that has only a rule to obey. Doesn't give you dynamics. There is no Hamiltonian. It's a probabilistic. It's a theory how to compute probabilities.
So it sounds like you are assigning some kind of non-local probability.
It is the
distribution.
highest.
Right.
This is the most non-local
Right. Okay.
probabilities that are consistent with no signaling.
Right. As opposed to quantum mechanics, it's some local way of assigning.
That's correct.
Property. Okay.
That's correct. And that brings you here. But we don't know yet to formulate one principle that says quantum mechanics. This is quantum mechanics.
But you equate that with causality.
Yeah, you can prove that this is non-signaling is the limit. So forget about this machine.
Right.
So I take the space of these guys, and I ask that the marginal probabilities are neutral. So I sum over all the settings, and A and B, and I have the reduced probabilities for Alice, and they should be neutral. There is no signaling. Whatever Bob does not affect here. So the constraints of non-signaling can be written as the marginals being neutral, and then you see that this is the limit. And then it turns that this implements that limit.
So in this way, somehow you're building in a maximum speed for information sharing.
No signaling is a word, because the maximum speed tells you that you can signal if you can send light, okay? So because everything in the frame of quantum mechanics there are no speed of light limit, so the non-signaling is only referred to space-like events. So you simply say that. Do not enter in the dynamics of sending the C. C does not show up here.
I see. So the notion of something in space-like, that's where you introduce
Yes, you have to introduce it.
Right.
Yeah.
Right.
So that's why typically you do things simultaneously. What I did in the beginning of writing rho of B from Alice and Bob instantaneously, because then there is no signaling, okay? And I don't need to do whatever the speed of light, I can always take an epsilon time shorter than that, and then my reasoning goes through. Yeah. There are very beautiful things, and if anybody loves this interplay between relativity and quantum mechanics at the very fundamental level, why there is no signaling, it's a beautiful experiment that Alice and Bob want to communicate faster than light. And the way they do it is by playing not with the state, but with the measurement apparatus. Okay, that's how they do it. I could write it if I had 10 minutes. I would write it for you. But what is a beautiful thing is that in order for the guy to decide what was measured in Alice, so take a singlet. Okay, so Bob then explores all the measurements to see what he gets to guess what Alice did. So there is a way to do that, provided you can copy the state. So no cloning theorem is at the heart of non-signaling. So if you ever, I don't know if you have gone through the no cloning theorem, it's one of the most profound ideas in quantum mechanics, the fact that you cannot copy a state, an unknown state. If you could copy, you could signal faster than light. That's never explained anywhere. It's very, very beautiful.
And if I just very quick follow up back to this square root 2 again. So from what you just said, let me ask you this question. Is quantum mechanics the unique way of distributing probability in a local way? Is quantum mechanics the unique way of distributing probability in a local way?
Well, the correlations that quantum mechanics delivers are more non-local than the classical, okay? That's a fact. And it is a very specific. The postulates were there, okay? Can you write other theories which are not like that? I give you the example. Write quantum mechanics as a path integral. Substitute the principle of the path integral by another thing over there, and you have another theory. The quantum mechanics is the one law that produces enough non-locality to be compatible with the experiments. Whether there are other ways of formulating the theory, I'm sure. Do you think that our way of building the models is unique? I don't believe so. I give you the example. Postulates von Neumann, postulates of Feynman to compute. Nothing to do, no operators, nothing, path integral. Completely different theories deliver the same correlators. So quantum mechanics is a model of computation. And it is consistent with other measurements. And we don't have reason to believe there is something beyond that. That's the message. Okay, lunchtime.